Alright, today we pick up where we left off last time. We talked about the basic principles of mechanical design, then we talked about stress analysis, and for the last thing we talked about was elongation under direct stress. So that if we have a uniform member under uniaxial uniform load P, the elongation is going to be PL over EA. L is the original length of the member. Now let's look at one example. So question is, if the problem is if you have a tensile force of 950 Newton applied to a 12 millimeter diameter round bar, compute the total deformation if the original length of the bar is 3600 millimeters. The bar is made from steel having a modulus of elasticity of 207 gigapascal. So the first thing, we can either directly use the elongation for relation delta equal PL over EA, or we can compute the stress P over A, and then we can compute elongation. For a stress, we have sigma equals P over A. We have a simple uniform bar, round bar, under tensile load P, and P is 950 Newton. The cross section of the bar, this is a round bar, so this is the cross section of the bar. The diameter is 12 millimeters. Then sigma is equal to P over A, so it is 950 Newton over A, and A is pi d over d squared over 4. Because we have the unit in millimeters, then with the sigma we compute is going to be in megapascal. And if you do the substitution, what you get is sigma is equal to 8.4 megapascal. So all we did was to use the basic relation for stress. We have a direct uniaxial stress. Sigma is equal to P over A. P is 950 Newton, and the diameter is 12 millimeters. So the stress we compute is in megapascal. Just be careful about the units. And then once you have that, you can go to the equation, the relation we had for elongation, which was PL over EA, or sigma L over E. You have sigma, you have initial length 3600 millimeter, and you have elastic modulus 207 gigapascal. So the elongation you get is, let me see, I had computed this number before, is 0.146 millimeters. All right. So we have a simple direct uniaxial stress case here. We had a round bar. The round bar was under a single axis tensile force, and then we computed the elongation of this bar. Next thing we want to talk about is direct shear. Essentially, it is the same, the way we define direct shear is the same as we define normal stress. It is force divided by the area. The only difference is about the kind of a stress we experience in this case. This stress tends to cut through the element, so as if you're cutting something using a pair of scissors. And all you do is P divide force by the area. The more correct way name for this stress is average shear direct shear stress. It is because we assume that we have a normal distribution of force across a cross section, and then we divide that force by A. So it is kind of an average shear stress. The next thing we want to talk about is torsional shear stress. So for a circular cross section, if you apply torque, then what you will experience is called torsional shear stress. Again, if you consider this pen, for instance, if I try to apply torque to both sides of this pen, what happens is different layers of this pen tend to slide relative to each other, and that's called torsional. What causes that is torsional shear stress. Just one thing. One side or important point is what we're doing here is we are relating an external quantity like torque or force to an internal quantity, for instance, torsional shear or normal stress. One thing here is that this stress varies linearly with linear distance or radial distance from the shaft center. We don't go to the details of this derivation here because what we want to do is we want to progress as fast as we can towards mechanical design. So what you need to remember is that this torque, T, is related to this torsional shear stress through this relation. Now, that J is called section modulus, and for a shaft, for a circular cross section, J is defined as pi over 2 c to the fourth, and c is the section radius. So you can rewrite that torsional shear stress in this form. You can just package J and C together and you can call it polar section modulus. So if you divide torque by polar section modulus, you get tau. Now, and if you recast your relation into this form, then it would look the same as a normal stress relation. So there we had force divided by area. Here we have torque divided by polar section modulus. And the last thing we want to talk today is torsion of hollow shafts. It is advantageous to, at least in terms of weight, you could see that if we use a hollow shaft, we are going to save material and we are going to have a lighter mechanical element or machine element. And if you do that, if you have a hollow circular shaft, the only difference would be in terms of how you compute J or your section modulus. All you need to do is you need to look at your internal diameter and your external diameters. And then once you have computed J, same as a solid shaft, you can substitute it in this relation to compute shear stress. Thanks for paying attention, and see you in next video lecture.